So it came all the way from the West Coast and landed on our door, I think at 1 a.m. But he did wake up. I managed to shake him up. So tell us about how fairness begets optimization and lots of other things.
Yeah, thank you very much, Ali, and thank you all for coming. So it's really great to be here. I was never officially a postdoc here at the IAS, but I never let that stop me. I snuck into the side door, and I feel like this place here, Avi in particular, played a huge role in my growth as a researcher. And it's a small group. I don't need to finish all my slides. If you have any questions, please stop and ask. My older academic sibling is here, and I'm sure he'll give you good answers. Okay, I'm going to talk about omniprediction and multigroup fairness, neither of which are terms I would expect you to have heard before. So what are we talking about here? So as we know, probabilistic predictions are all around us. They influence what movies you watch, what people you meet, medical decisions, college admissions, and lots of things. And of course, it's hard to deny that this has been very successful and impactful. It affects all our lives. But of course, as Spider-Man's uncle told him, with great power comes greater responsibility. So it's fair to ask, we're making all these probabilistic predictions. Here's the probability you have a certain condition. Here's the probability you'll finish college. For you guys, I think the probability is pretty high. But what do these probabilities really even mean, right? And when you're trying to model some complex phenomena, like the probability that someone gets a certain medical condition, it's very fair to ask, what is the model of nature that is being hypothesized here? These are all very basic questions. And it's fair to say that, we don't have good answers to these, especially with the kind of deep neural net models that are being used these days, right? When you ask this question, it naturally brings up the question of what is the guarantee here that these probabilities are correct, that they are fair? Like, for instance, if a doctor tells me that I have a certain risk of heart disease because of my prior conditions, what exactly does that mean, right? And to get at where all these probabilities are coming from, this question is basically asking, how are we training these models? And how models are trained these days is through loss minimization. Right? There's a ton of compute happening this very second as we speak, where we're taking these huge models and trying to minimize a certain loss by doing some kind of gradient descent. So that really is the core of where all these probabilities come from. So we need to look at this notion of loss minimization more closely and ask, what really is it getting at with regard to each of these questions? This is something which many people in our community have been doing over the last few years. And this is the context in which everything that I say today is going to sit. Right? So I'm going to start by defining loss minimization just from, I'm sure you've all seen this before, but just so that we have common context here, I'm just going to start by defining loss minimization. Right? So we're going to talk about the context of supervised learning with binary labels. What this means is that there's a joint distribution on points X, which are some attributes we know about the population. And then there are labels Y. For this talk, for most of this talk, the labels will be binary, 0, 1. Does this person have this condition or not? Okay. Now, the moment you assume a joint distribution, this implicitly defines something which we call the Bayes optimal predictor, which is, given a point X, what is the conditional probability of the label being 1? Right? So this is what we would think of as nature or the ground truth probabilities for this distribution. A predictor is just any function which takes points and assigns probability of the label being 1 to these points, right? So we're going to denote this by P twiddle and just call it P, maybe, to distinguish it from P star, which is the Bayes optimum. So when we are learning, we are trying to approximate nature or the ground truth. Now, the ground truth is very complex, it's unknowable, so we come up with some tractable approximation. This is what learning is about. So in what sense are we approximating the ground truth? That is the question we want to know. Right? But so let's draw a picture. So predictors are just functions from X to the interval 0, 1. So this is a nice space. It's closed under convex combinations and so on. So predictors really are just points in space, and you can take convex combinations of predictors, get other predictors, and so on and so forth. The ground truth probability, P star, is again some function in the space, but it's a very complex function. We don't expect to figure P star out exactly for computational and information theoretic reasons. So how do we cope with this? Well, what we do is we come up with a nice structured set of models. These could be decision trees, they could be deep neural nets, or any set of models, right? They might be closed under convex combinations, but they may not also be. Like things like deep neural nets, decision trees, they're not really closed under convex combinations. And then we choose a loss function, right? And we try and minimize the expected loss of models in this class under the distribution D. And this gives us our best model. So this is worth pondering for a little while, right? We took some loss function. I'll define a loss function more formally just on the next slide, but this is what we're doing. We're taking a loss function, we're looking at the expected loss, and we are picking the best model in C under this expected loss and saying that's our model of nature. So what does this really mean? What are we doing when we do this loss minimization? Okay, so in loss minimization, there are three characters. There's the distribution D, which we already talked about. There's this tractable class of hypotheses, right? So I'm allowing hypotheses which take values in -1, 1, rather than just 0, 1, which is what a predictor should do. But you can ignore this difference. A loss function now will take two arguments. One is a label 0, 1. The other is this parameter T, which I call the action, right? So it's like, well, let's imagine that this is some kind of a medical thing. The action we are proposing is something like, give them aspirin, catheterize them, do some very invasive heart surgery. These are all actions. Then we come to know, we take the action before we know what the label is. Then we come to know what the label is, and accordingly, we have a loss function. For example, if someone was in a serious condition and you said, give them aspirin, that's not so good. On the other hand, if someone was just fine and you decided to do an invasive surgery, that's not good either, right? So the whole challenge of learning is to take actions before you know what the label is going to be. Okay. Loss minimization, what you do is you pick the hypothesis class, which minimizes this expected loss under the distribution D. Now, convex losses, we're going to say that for this portion, a loss is convex if the second argument, you allow for real values, and it's a convex function of these real values. Okay.
And the reason to think that in the medical example you gave, this is convex?
No, I said a loss is convex if this is, so, you're right.
In which situations is convexity relevant?
Yeah, so, the kinds of losses that we try, let's come to this in a second, right? Convexity, you're making a good point here. There are two things which need to be convex. One is the loss function. The other is the class of models themselves. Often, things like squared loss, cross entropy loss, these are very reasonable loss functions. They happen to be convex. But in the real world, when you're doing things like deep neural nets, there's also the parameters of this model. And that's usually where a lot of non-convexity creeps in. Right?
But even in the first example, I realized that,
Right. No, you're right.
Squaring or entropy, but the parameter you represent heart surgery or aspirin with a number.
If you're okay with randomized actions, then it's convex.
Well, but I take Avi's point.
Usually you take an action. You don't give aspirin with copy. You go to a doctor, that's not what happens. Judge.
I think Avi's point is that in the example I gave, the space of actions is a discrete space. It makes no sense to talk about convexity there, and that's very good. But often, when models are trained, people are minimizing these convex loss functions. Okay. So let's give a few examples of loss functions. So I'm going to divide the space of all loss functions into two classes, proper and non-proper. Proper losses are things like the squared loss, where, the squared loss is something which is very familiar to us. When you have a label y, you make a prediction p, your loss is y minus p squared. Right? Another one.
Why is still a bit here?
Y is a bit. Yeah. So suppose you predict 0.7. If the label is 1, you'll have to pay 0.7 squared. The label is 0, you'll pay 0.3 squared. Right? Cross entropy loss is basically, what is cross entropy loss doing? If the label is 0 and you predict a very high probability of the label being 1, you'll be penalized for that. Conversely, if the label is 1 and you predict a high probability of being 0, you'll be penalized for that. There's a certain formula. It doesn't really matter. It's convex in the parameter p. What is unique? What is this proper property? The proper property says this. If you really believe that the label is going to be drawn from a Bernoulli distribution with probability p, your best strategy is to just tell the truth and say p. Like, you freely express your beliefs. That's the optimal strategy. This is what a proper loss is. In contrast, there are non-proper losses like the L1 loss. In the L1 loss, when the label is y and you predict p, you'll pay the absolute value of y minus p. So for example, if you predict 0.7, the label is 1, you'll pay 0.3. If it's 0, you'll pay 0.7. Right? Logistic loss, it's some loss function. It's non-proper. That's the only thing that matters. So what is the defining property of these losses? If y is a Bernoulli random variable with probability p, you may not necessarily want to say p exactly. You might want to do something smarter than that. For example, for the L1 loss, if you believe that the label is being drawn from a Bernoulli distribution with parameter 0.7, easy exercise, you should say 1. If you believe it's a Bernoulli distribution with parameter less than half, you should say 0. Right? So the optimal action is some function of the probability p, which is not the identity function. Now, having made this big distinction, I'm going to say that really, let's forget about non-proper losses and just think about proper losses. The reason is that I can tell you, instead of taking an action, you tell me the probability. I will choose the best action for that probability. And this composition essentially becomes a proper loss. Right? So having made all this noise about non-proper losses, I'm going to tell you, you can kind of really think just about proper losses. The problem with this is that if you have some nice property like convexity, you might lose it when you do this conversion. Right? Even this L1 example will show you that. Okay, with all this set up, now let's go back to the big picture. When we do loss minimization, in what sense are we approximating nature? Right? Before that, let's convince ourselves of one thing. If you're doing loss minimization, the ideal thing is to figure out the base optimal predictor P star. You cannot do better than that, no matter what loss you care about. P star is the ultimate answer for loss minimization. Why is that? Well, given X, if you knew P star, you know that the label is now being sampled as a Bernoulli random variable with a certain probability, right? So now you can optimize, in some sense, the uncertainty is you don't know what the probabilities of the two variables are. If someone whispers it in your ear that tomorrow it's going to rain with probability 0.7 and not rain with probability 0.3, choosing optimal actions for any loss, it's a breeze, right? There's this optimal function that you can take that we just talked about. You can solve this optimally. So if you knew P star, by composing it with this optimal action function, you can do better than any class of hypothesis for any loss function. Right? So this is a very powerful loss minimization guarantee. This is something that we will formalize by the notion of an omnipredictor. I haven't defined this yet, so this statement makes no sense to you right now. It's just jargon, right? So this very powerful loss minimization property, that this one predictor is optimal simultaneously for every loss function compared to any baseline, is a term that we'll call an omnipredictor. But that's getting ahead of ourselves in the story. If you knew P star, life is good. You can optimize any loss. But typically, we optimize over a very limited class of hypothesis C, and not even the most wildly optimistic machine learning practitioner believes that these will really contain P star, right? So if you're just minimizing over P star, then what are we doing? What is the model of nature that we are coming up with? It turns out that there's a nice geometric picture you can draw here. You can think of it as a certain projection in the space of something called as Bregman divergences. So for those of you who might not have seen Bregman divergences before, this includes things like squared loss and KL divergence. It's some kind of a geometry. It's not really a metric, but it's close enough, right? It turns out that when you minimize a proper loss over a class C, what you're really doing is finding the model within this class which minimizes the Bregman divergence from P star. Extremely reasonable, extremely rigorous thing to do, right? And the issue is, suppose you're minimizing each loss function that you think of, each proper loss function that you think of, it endows the space with its own geometry, with its own Bregman divergence. So suppose you minimize loss L1, it's going to tell you that this model is optimal. Suppose you minimize loss L2, it might tell you that some other model is optimal. If you minimize L3, it's going to tell you probably that yet another loss is optimal, right? Because each of these things, it corresponds to putting a different geometry on the space. And why should the closest thing be the same, right? Empirically, you take a problem, you run least squares regression on it, you run logistic regression on it. Both of these are minimizing, reasonably, or you minimize some of the proper loss, KL divergence assures cross entropy loss, not logistic loss. These are both proper losses, but you'll not get the same predictor. You'll get different predictors, right?
So what, I mean, it's a much higher level.
Yeah.
What were people doing? I know you guys are looking now at a family of losses and, because you got to restore the omnipredictors and so on. I mean, was this common? I mean, in optimization, typically people pick their, pick the loss function they minimize. They pick the optimization problem and then try to, where does it occur before, the 50 years of optimization?
It manifests itself in scikit-learn, where, when you're trying to optimize, you have a laundry list of 10 different loss functions that you could choose to optimize. And if those are not good for you, you can define your own loss function.
Yeah, but how do you pick between them? Or are you trying
empirically?
You try them all and see what
if they say this thing is stable, this has some other nice properties, cross entropy is good because of this, but then, maybe in some other situations you want to try this other loss and so on. I wouldn't say there's a lot of science there. It's kind of, to my view at least, which is fairly limited.
Because you sell systems to hospitals, you sell systems to how do you argue that, I don't know, the loss function I picked
that whole conversation happens in terms of train and test error. This is kind of the end all and be all, that we got 95% accuracy. But of course, there are shortcomings. What if this 5%, there is some systemic problem there, that is a certain population that you just always are getting wrong, and you shouldn't be at 95, you should be at 99. There's no answers to any of these things. And this is where multi-group fairness came in, saying like, let's look a little bit. You cannot reduce something as complex as this to a single number, right? That's where it came from. So, but honestly, I mean, the world of machine learning is very comfortable with having 1,000 hyperparameters, which only which you pull it out of thin air, and which loss function to optimize, what optimization algorithm you use. Well, this is all magic sauce. It's not a very satisfying answer, but that's that. Okay, so loss minimization, to summarize this part, there is a reasonable geometric explanation behind what's going on. The unsatisfactory part is that each loss gives you its own geometry and it gives you its own optimum, right? Now, you could very reasonably think that, So every loss is giving you its own geometry and it's resulting in its own optimal model. You could very reasonably say that each of these models is perhaps picking on some aspect of nature which it models particularly well. But, then our friends over in physics would ask us, well, so do we have one explanation which summarizes everything you learned about nature by training on all these different loss functions. And my belief is that prior to our work, there wasn't a satisfactory, even theoretical language for talking about notions like this, right? To give an analogy, it's like the poem where you're trying to understand this big complex creature, which is nature, but each loss is giving you this local view. This is the tail, this is the ear, this is the leg. How do you synthesize this together and come up with this one model that summarizes everything you know about nature? So this is the notion of omniprediction, right? Which was introduced in joint work with Adam Kalai, Omar Reingold, Vatsal Sharan, and Odi Wieder. It posits a unified path to P star, to approximating P star, in a fairly obvious way, given what I've said. You say for a family of loss functions, L, and a hypothesis class C, an L, C omnipredictor is one predictor, so that for every loss in this class, the expected loss you suffer when using the omnipredictor is less than the minimum loss you would suffer by choosing the best hypothesis from the class C tailored to this particular loss. So that's a lot here. So let's unravel this definition. There is this predictor P tilde. You train it once and for all without knowing what loss you're going to evaluate it against. You only know it belongs to some broad class L of losses. Okay. Then after you trained it, you throw the data away. You are done. Right? Now the loss L is revealed. There's an adversary who now runs stochastic gradient descent or whatever and finds the best hypothesis from C tailored to this particular loss. Right? We need to know the loss to the extent that we need to know how to post-process our predictions. Like if it's L1, we'll do the rounding. If it's L2, we'll do nothing. If it's LP, we'll do something else, and so on. But this does not require training again. You threw the data away. You are done. You just say, what loss do you care about? Okay, here's what you do with the predictions. You post-process them in this way. By doing this, you are getting better expected loss than an adversary who is retraining on C every time and finding the best hypothesis suited to this particular loss function.
Is there any reason to believe, I know you have one, but is there any reason to believe a priori that there is such a
Yes.
P star?
P star is good, no?
P star.
Oh, no, P star, so yeah, P star is good. That this it can be found by training.
Good. That's the whole question.
Yeah,
that was the whole.
P stars, that's right.
Yeah. So the whole question here, obviously, as usual, you're one slide ahead. It's a computational question. Its existence of these things is follows. Yeah.
So this P tilde is deterministic. It cannot have any randomness.
Yeah. Let's say it's deterministic. I mean, it's this is with probability 1 minus delta. You get an algorithm which predicts. Yes.
Expectation on the left is not about the choice of.
No, it's only under the distribution. Let's say we have an algorithm which works with probability 0.99 or something.
So not to get too ahead of your slides, but the answer clearly depends on like the family of loss functions. So you have to like specify. Is the computation question going to be like, how you specify the family of loss functions and stuff like that?
The question really is whether we can. Okay, so let me finish this slide and let's see if we have good answers to both your questions, right? Okay, so the reason why this is interesting is it's really about learning once. It's kind of learning agnostic to the loss function, as long as L is sufficiently big and reasonable, right? And we're competing against an adversary who would know the loss function in advance. I said that already. If you consider only a single loss function, this is basically agnostic learning, right? We're saying we want to do as well as a base class. But now we're saying, well, let's broaden the scope of L's that we can handle. Now, to answer Avi's question, there exist omnipredictors. P star is an omnipredictor for all L, all C. Fantastic. The question really is, can we learn omnipredictors efficiently to answer Pravesh's question for rich classes of loss functions L? If I give you an omnipredictor which works for the L2 and L4 loss, you're probably not going to be very impressed, right? So the whole question is, what does it take to get omnipredictors all at once for broad classes? Like we want to do convex loss functions, Lipschitz loss functions, I want to be able to do well on loss functions I've never heard of. If you have a loss that you care about it, I will not judge you. If it fits my template, you can use my predictor and make good decisions based on that.
So you want the predictor to be in some class containing C, but not much bigger, or something
Exactly.
small combinations of things from C, or
Yes, the complexity theorist in the audience is, the complexity of this class relative to C. If Sanjeev were here, he'd say you're just doing boosting, and it's kind of true. It's going to be something, it's kind of a pseudo-randomness thing, right? Something a little more complex than C. Okay, so this is the question. Can we efficiently learn omnipredictors? I've said rich L and C, but I really mean rich L, because we'll abstract away the complexity of C by some basic learning primitive, as you'll see. So this is the question. You know now one topic from my title, what omniprediction is, what the main question here is. Now let's segue to multi-group fairness. And really, my interest in fairness, to me, fairness is really a notion of pseudo-randomness. In this room, this audience, that's the right way to put it. Let's start off with accuracy in expectation and calibration. These are what we call what is fashionably called interpretability notions. These get to the question of, well, you're predicting probabilities. In what sense are these probabilities? Do they pass some very basic tests? The most basic definition is accuracy in expectation. Imagine a weather forecaster who's trying to predict the probability of rain in Princeton every day of the year. Right? Now, this predictor is accurate in expectation if over the length of the year, if it rains 10% of the time, their average prediction is also 10%. This could happen in many ways. They might actually predict 1 on 10% of the days and 0 the rest of the time. They might predict 0.1 every single day of the year because they know this is what happens on average. They could do anything in between, right? This doesn't even mean that they are good. They might predict rain on 10% of the days which happen to be bright and sunny. That's fine. All we want is that the expected prediction, which is expectation of a real valued random variable, should equal the expected label. That is accuracy and expectation. Okay. Then there's this very nice and simple notion of calibration, which I'm sure many of you have seen before. It goes back at least as far as 1984, the work of David. Calibration says that you should be accurate in expectation, conditioned on the prediction probability. What exactly does this mean? Let's go back to this weather forecaster example, right? What we want is that when the forecaster says 0.1 probability of rain, it rains 10% of time on those days. When they say there's a 20% chance of rain, it should rain 20% of the time. When they say 90% chance of rain, it should rain 90% of the time, right? So conditioned on their predictions, that is what you see, right? In some sense, we are asking for predictors to pass some very basic sanity checks. If when you predict rain 90% of the time, you only see rain 60% of the time, then there's a very simple improvement you can make. Switch 90 to 60, right? And this is saying that at least these sanity tests you should pass. So let's point out that these people who believe in the religion of loss minimization have a hard time with these notions because these are orthogonal to any notion of accuracy or goodness of a predictor. For instance, we talked about, suppose it rains in Princeton 10% of the time. The God themselves, who predicts exactly what's going to happen on every day, is calibrated. But a lazy old weather predictor, who just predicts 0.1 every day of the year, is also calibrated because when they predict 0.1, it does happen to rain 10% of the time, right? So calibration is kind of this weird self-referential thing where if you posit a more complex view of the world, I will subject you to a more rigorous test. If you say on these days it's 0.47, on these days it's 0.48, I want to know why you're differentiating between these. Is it really 0.47 and is it really 0.40? Okay. So by the way, calibration is it's a really subtle notion, and I have a whole line of work which aims at understanding this notion, defining it properly, and so on. But fortunately, you don't have to hear about that today. Let's talk now about multi-accuracy and multi-calibration. These are multi-group fairness notions, which were introduced in this very nice paper by Hebert Johnson, Kim, Reingold, and Roppler. They were interested in multi-group fairness. So the thing I want you to keep in mind is that this is medical data. We have various demographic subgroups, people over a certain age, people with a certain history of medical conditions, and so on, right? And you really want predictions. Just saying that this works on average 95% of the time, as I said, is not good. You want predictions which actually take into account the diversity of the population. And conditioned on each of these attributes, on all of these attributes, you want good predictions.
Also, medical experiments in the last 100 years say that something works means it's applied to male.
Yes, yes, yes. And this is one of those, what in my view makes this a very good definition is that when you talk to people in the medical field, it really captures something that they struggle with all the time. Like, when I take my kids to the doctor, they say, oh, they're skinny, they're underweight, but well, they have certain, they're my kids, so there's a certain prior there. Are they calibrated for that? And they realize there's issues with these, which they don't have either the data or the vocabulary to fix, right? Okay, so really this definition in the fairness worldview, it says that I want accuracy and I want calibration conditioned on each of these subgroups. I wasn't planning to say a whole lot about why this is a fairness notion, but maybe because people haven't seen this before, let me just say this very quickly. Like this, it's very obvious that you're trying to get something, like let's go back to a weather predictor, right? So we don't want this, we want to get rid of this lazy forecaster who just predicts 0.1 all year long sitting on the couch. So how can we make them, how can we elicit more information? I'll say, well, I want you to be calibrated on days when the temperature is high. I want you to be calibrated for every month of the year. I want you to be calibrated when the humidity is a certain level. I want you to be calibrated when it's been raining the last 4 days. Now you cannot just say 0.1 and expect to be calibrated, right? Because clearly if it's been raining the last 4 days, there's probably a good chance it's raining today as well, right? So this is trying to nudge the predictors in the direction of the Bayes optimal by extracting more and more information out of them. Okay. Why is this relevant to fairness? Well, let's imagine this is the whole population. Let's say that this is a predictor that we have made. We are giving it to a bank who's going to make loan decisions based on our predictions. Okay. Now, here is a subset C that we want to protect, right? It might be, think of your favorite protected subgroup. What does calibration mean? What does multi-calibration mean? If C is in one of the protected sets, when I say the probability of, so, I'll stratify the set C, I'll give risk probabilities to various populations. Now, when I say the probability of default is 0.2, right? Calibration guarantees that it is 0.2, conditioned on being in C, and also conditioned on not being in C, right? So in some sense, a bank who only cares about minimizing the expected loss should just take my word for it and not probe into does this person belong to C or not. On the other hand, if it's not calibrated, right, then if this is the 0.2 set, what might happen is that if you're in C, it's actually 0.3. If you're outside C, it's actually 0.1. So a bank who's not necessarily trying to be bad, but only wants to minimize their expected loss, now has an incentive to find out about membership in C and treat you differently based on it. So there's a lot of debate in this community about, oh, is this the fairness notion? I think this is a mistaken debate. Fairness is a very complex thing. There cannot be one notion that fits everything, but it's completely obvious why this is a good notion. And if you're putting out predictors which are not multi-calibrated, you better have a good reason, you better have thought through what the consequences of doing that are. Anyway, as I said, this is not a talk about fairness, so let's get back to.
Can I ask a question?
Yes, sure.
Though, like when you say multi-calibrated, you always mean multi-calibrated with respect to some
Yes, I was going to say that, sorry. So the collection of C of subsets is very important here You cannot get multi-calibration with regard to every subset. You cannot get multi-calibration with regard to individual points, for instance. That's basically saying you want to know the base optimal. That we cannot do. So the collection of subsets plays a key role here. I'm going to generalize the subsets to be real valued functions. So this is based on a couple of previous works, one by Ghorbani, Kim and Zhu, the other the Omnipredictors paper. Here's the definition. We say that a predictor is C alpha multi-accurate if you look at the residual predictions, y minus px. Think of these as the errors of your predictions. This is asking whether anything in C can find a pattern in these errors, whether you can find correlations. If you cannot able to find correlations, then you're multi-accurate.
This is a pseudo-randomness.
Yes. This, I should say that this has been studied in many works, in particular the dense model theorems of Trevisan, Tulsiani, Vadan. This notion appears there. What is multi-calibration? Multi-accuracy, but now conditioned on the prediction value. You look at the prediction, condition on the prediction of 0.4. You look at your residual errors. Nothing in C should be able to find correlation, find a pattern, right? This is multi-calibration. Now, to go to Yotham's question, the whole question is, what subset C can you achieve this for? Or what families of functions C can you achieve this for? The answer from this very nice paper is that it's efficient, provided you have a weak agnostic learner for C. Right? What the heck is that? It's basically being able to audit for this condition. If there is a correlation, if there is something in C which has correlation with the errors, you're able to find a witness. It need not be the optimal witness. You're just able to find some witness and say, look, hey, this is, there's a correlation here between this function and your residual errors. So clearly your model is not correct, right? If you can just solve the auditing problem for multi-accuracy, you can boost it all the way to get an efficient multi-calibrated predictor.
This will be the distribution specific boosting here.
Yeah, very good. Yes. You can do boosting by branching programs, Mansur McAllister. So that was one of the things we did in the Omnipredictors paper. In some sense, we knew that this boosting by branching programs thing is very powerful. We didn't quite have a crisp definition, so what the power is. And in hindsight, I would say that that gives you multi-calibration, whereas previous boosting algorithms were just giving you multi-accuracy. Okay, so what is the view of nature that multi-calibration puts forth? It's a very clean model of the world. You just take the space, you segment it into regions. Here is where I predict 0.1. Here's where I predict 0.3, 0.5, 0.7, 0.9, and so on. And then you say that within each of these regions, what's going on is very simple. You just toss a Bernoulli random variable with parameter 0.1 over here. That's how the labels are assigned. Here you toss it with probability 0.3 and so on and so forth, right? This is the worldview that multi-calibration puts forth. The guarantee it gives you is that correlation tests from C. This is a class of tests which it says, well, okay, you're predicting 0.5. Let me see if I believe that. And how do you do that? You check for correlation, or more precisely for covariance between C and the label. It's covariance because Y might be biased, okay? So this is the worldview this is multi-calibration's view of nature, right? So this picture, I think, is a very important one. There's been I don't know about 1,000 words, but there's been a few really nice papers written on it. A very recent work that I really like by Casacuberta, Dwork, and Madan says that you can get Impaliazzo's hardcore distribution just from looking at this picture the right way. But
those cases, C is just a large set or something. You didn't specify here what C was.
Oh, okay. To be C multi-calibrated means this. You full test from C, right? So multi-calibration, it scales with the complexity of C. If I ask you to come up with a multi-calibrated model for a very weak C with just constants, it's probably very easy to do. As the complexity of C, this goes to Zev's question. As the complexity of C goes, you will have to work harder and harder. You'll have to come up with a more nuanced model to be multi-calibrated, right? Sorry. there's always a C here. This is a C multi-calibrated partition. That's a partition where within each of these things, you'll fool all correlation tests from the class C. So I keep ignoring C, but the notion of multi-calibration, it's C multi-calibration. C is always implicit there. If C is just conjunctions, this is probably not very interesting. If C is deep neural nets, then that's great, right?
Yeah, but in particular, you're not telling us which C this can be.
I
efficiently
kind of
found.
told you that because I said that you can get this as long as you have a weak agnostic learner for
Okay,
C.
yeah.
Yeah, so I just abstracted that away. Look, weak agnostic learner is a very basic primitive, right? It's kind of saying you at least got to tell me whether my model of nature is correct or not, right? If you cannot even do this much, then I can present you with the model and say, hey, this is nature, and you wouldn't know the difference, right? As long as you're able to do this auditing for C, we can boost it all the way to get a multi-calibrated partition. Now you could ask what classes C can we actually do weak
Yeah,
agnostic?
but I mean, maybe harder to find the C for which it doesn't work.
That is what weak agnostic learning is supposed to do.
Also, weak agnostic learning will find a correlation
Yes,
with some C in the class so that
Correct.
which will violate your promise.
exactly. So C, it's finding a witness. So maybe I should stress this a little more.
So give, just examples of families for which this happens and examples where it doesn't.
Okay. So, firstly, I should say there are classes of Cs for which you can, for example, if Cs were parities and you were working with the uniform distribution, we know how to find correlated parities, right? This is Hadamard list decoding. That's an example. For things like deep neural nets, there is no way in the world you'll get theoretical results like this. But I also think that a weak agnostic learner, it's a good abstraction of a heuristic. It's saying that, look, if there is something which achieves correlation 70%, you find me something which at least does 51%, right? Which does something better than complete junk. And that's all I need, right? So, yeah, you're asking a good question. We have formal results for things like kernel functions and so on, which, for those things under any distribution, you can do this weak agnostic learning task. But I think of this more as an abstraction of, okay, for decision trees, you believe that some kind of forming stumps is giving you something correlated, you can use that as a weak learning.
So actually, there is a reduction from weak agnostic learning to just testing if there is a problem, like testing if there is a function in your class that witnesses like the lack of multi-calibration.
Right.
So it is literally just if you can test, if somebody can tell that your predictor is not multi-calibrated, then you have an algorithm.
I see. I didn't know this. So you're saying that you can automate this finding.
So this is a paper that Roy and I wrote while being at the IAS many years ago.
Okay. I didn't take that out of this paper, but that's very cool. Well, clearly I'm giving this talk.
There was no multi-calibration.
Yes.
Okay. So here is the main result from this paper. It's a connection between this notion of multi-group fairness and this very strong Omni prediction result. It says that let LCVX be the class of Lipschitz convex bounded losses. This is every reasonable loss function that people typically care about. If your predictor is C multi-calibrated, then it is an omnipredictor for this class of convex bounded Lipschitz loss functions. Okay. So what is this theorem saying? We can think of this as a game between a predictor P and an adversary A. The predictor comes up with this partition of space, which is their multi-calibrated, which is their C multi-calibrated prediction. The adversary then gets to choose a loss from this class and a hypothesis C, which maybe is tailored to this loss. And they see who has lower expected loss, right? And of course, the response of the predictor has to depend on the loss function. You do this post-processing. And the multi-calibrated predictor has lower expected loss as long as the loss is being chosen to be a convex Lipschitz loss function. Right? This is basically what the theorem says. Okay.
This is Plato and Aristotle.
I'm sorry?
Plato and Aristotle.
DNA, yeah. We have an art connoisseur in the audience. Okay. So why is this, I'm presenting this as a meta algorithm, which allows you to optimize for a large variety of loss functions. So is this a straw man, or are there really algorithms which we are unifying? I claim that it's the latter. If you wanted to do L2 loss, you do linear regression. That's covered by this. If you wanted to do logistic loss, you do logistic regression. That's also covered by this. L1 loss, it shows up quite naturally when you're dealing with Boolean labels. This is a beautiful result by Kalai, Clivans, Mansoor, and Servideo on agnostic learning of half spaces. It says that L1 is sometimes more noise stable than L2. It's a convex loss, so of course you could also, a multi-calibrated predictor takes care of that. Exponential loss, Adabus, Freund, and Shapire, also convex, also covered by this. I could go on and on. Well, actually, no, I don't know any other loss functions, but I will say that all the loss functions I know of are convex, so this one result covers them all. The other fact here is that, somewhat surprisingly, convexity is essential for this statement. Multi-calibration will not give you omnipredictors for non-convex loss functions. Okay. Okay. Let me sketch the proof for you. And when I say sketch the proof, I mean it quite literally, right? So some of you have seen a version of this proof from 2 years before. I'm hoping you've forgotten and I can impress you all over again. Okay. I'm going to make some simplifying assumptions. One is that the ground truth probabilities P star are Boolean, right? So nature either decides that it's going to rain today or it's not going to rain. We of course, we can never tell whether nature is Boolean or not. I'm just doing this so that pictures are easy to draw. Nothing important changes here. I assume perfect multi-calibration, which means that there is no correlation between C and the conditional decisions. Okay. So now, if C wants to beat our multi-calibrated predictor, it needs to be able to refute our view of the world, right? Our view of the world is that there are these partitions. Within each partition is just Bernoulli coin flipping that's going on. C needs to be able to refute this and to use that to its advantage. How could C do that? Well, this is the ground truth. This is the partition where we're predicting 0.7. What nature is doing, being Boolean, is that it's plus some fraction of the time, minus some fraction of the time. And because we're calibrated, it's 70% of the time it's +1 and 30% of the time it's 0. Okay. All right. So now, the omnipredictor.
Second, what you are assuming and what you want to conclude from.
Good, good. I'm assuming that I have a C multi-calibrated partition or predictor. I'm trying to prove to you that for any choice of convex loss and hypothesis C, the adversary cannot get lower expected loss than my omnipredictor. Right? And we're going to do this.
Positive somehow. If they can, then you could show that it's not multi-calibrated.
Basically. But, convexity better enter the picture.
Yeah.
Right? Okay. So now I'm focusing on one single partition where the predictions are points. Okay. So I'm just predicting, my omnipredictor is just predicting 0.7 for every point here. It says I cannot tell these points apart. C, of course, need not do that. C can differentiate between the various points in this region, and it has to in order to do better than the omnipredictor. So on some points, on the plus points, C will say something, on the minus points, it will say something else. Here's the thing though, once we fixed the label, we know exactly what the loss function is. It is just a convex function of the action that you take, right? In squared loss, if I tell you y minus t squared, if I tell you the label is 1, then the function you're going to be penalized by is just 1 minus t squared, which is the convex function. If it's 0, then it's t squared, which is a different convex function. But within each of these regions, you're just being penalized by a convex function. So now what do? Well, you appeal to Jensen's inequality and you say that, you know what? C doesn't need to predict wildly different values within each of these regions. It would be better if C just took the expectation of these points and predicted it everywhere for the 1 points. And it would take the expectation over the zeros and predict it everywhere for the zeros. Of course, C doesn't know the label, so it's not able to do that. But we're just doing this analysis in our head and saying the loss that C suffers is greater than the loss that would be suffered if you did these predictions, right? Here we use Jensen's inequality and convexity. But now multi-calibration enters the picture. Could it be that the expectation of C conditioned on the label being 1 is wildly different from the expectation of C conditioned on the label being 0? Well, if that were the case, you'd have correlation between C and Y. This is just a 2-line exercise from the definition. So multi-calibration tells us that these two conditional expectations, they were really not that different. We could have just predicted expectation of C everywhere and done only about as well, if not better. But now, so this is because of multi-calibration. But now we are in a situation where C is not distinguishing between various points in the partition either, right? And if that is the case, we know what the best value to predict is. It's what the omnipredictor is predicting. Right. So basically what we do is we take a C which predicts a lot of different values, use convexity to reduce it to predicting just 2 values on this partition, and then use multi-calibration to say that it should only be predicting 1 value, which is the expectation, and then saying that I have the best 1 value, so I'm doing better than C.
There is no boosting happening here.
No, this was boosting happened, we got this partition, and then we're saying, look, it's really giving you something extremely powerful. The germs of this idea, you could, with the benefit of hindsight, go back to Mansour McAllister and they say, oh, look, there's so many different potential functions that you could use here and so on. But I think a lot of this is about the crispness of the definition, right? Okay, so if there are any questions, feel free to ask. All right. So, okay, let me just say that, what's going on here in the original picture, you can actually fit this in very nicely. For proper losses, you can actually prove a statement of this kind, saying that this is really the picture that we are getting. Our multi-calibrated predictor is in some sense, it's on the shortest path to P star according to any divergence, fragment divergence that you choose. They have to be such that our theorem applies to them. But then any model which wants to minimize the divergence to P star might as well minimize the divergence to a multi-calibrated predictor. It's the same thing, right? As a Pythagorean theorem here. So I'm pointing this out to say that this is a very nice relaxation of trying to get to P star, which really it's kind of unifying what you'd get from different loss functions. Okay, so let me just let's digest what happened here. Multi-calibration implies the strong notion of omniprediction for all convex loss functions. It's somewhat surprising because multi-calibration, originally the motivation came from fairness. We can think of it as a pseudo-randomness notion, but the fact remains that it doesn't make any mention of loss functions, be they convex or otherwise. Secondly, this is a somewhat serendipitous first statement to prove on this subject, because a lot of statements in the epsilon neighborhood of this are false. Or either they're false or we don't know how to prove them. For instance, if you say non-convex loss functions, then the statement is false. If you put multi-accuracy here, that would be false. If you say, I don't care about all convex losses, I only care about LP losses, or maybe I only care about L2 and L4, I don't know anything simpler than multi-calibration. This is one big tool that we have. It's a hammer. It works for a large class of loss functions. We don't know how to scale it down. Right? So when we first proved this, even among the authors, we were somewhat surprised by it. Omar always sees the big picture, and he said he thinks of this as good karma. You're trying to do the right thing from a fairness perspective, and you get this very strong loss minimization guarantee. Right? My view was less philosophical. I had a simple explanation. I said, well, it must be that this statement is also false, and there's a bug in our proof that we haven't found yet. But it's been a few years now. Nobody has written to me with the bug, so it seems like it's true. But then it suggests that there's maybe some bigger picture here about why there is this connection between multi-calibration and loss minimization, and we need to look for it, right? Okay. So let me just tell you a few questions that I would like to talk about next. The first one is, is multi-calibration, in fact, why did multi-calibration show up? Is it necessary for omni-prediction? Then second, we are thinking of multi-calibration as a pseudo-randomness notion. And naturally, you could ask, is there a more direct indistinguishability-based proof or based explanation really for what's going on here? What happens if you care about other loss functions, other settings like the online setting, regression, and so on and so forth? Okay. So let's ask this first question. Is multi-calibration really necessary for omni prediction? Why did multi-calibration show up here?
You can take a break if you like.
I know, I was thinking in about 10 minutes.
Yeah, whenever you want, yeah.
I think you would need the break more than me, but I have a logical break point, so maybe 10
The
minutes.
speaker decides.
Okay, yeah. So we'll go till 3 o'clock and then we'll stop. Okay, so is multi-calibration really necessary for omni prediction? I'm going to put that on stack and introduce this new definition called swap omni prediction. This is with joint work with Kim and Reingold. Gopalan is me. Okay, so we go back to our picture where we have L and C again. A predictor P comes up with this partition. And now the adversary is more powerful. For each prediction, the adversary picks a loss function and a hypothesis and says, beat that, right? So they are allowed to look at my predictions first and then suggest a challenge, L, C, pair, for that particular region of space. Now, of course, they will do a best response to each of the loss functions, right? And in fact, I encourage you to fix the loss function. Just think of adapting C to each and every partition. That is already a very powerful adversary to go up against. We will say that a predictor is an LC swap omni-predictor if no adversary means no strategy of L's and C's here, has much lower expected loss. Okay? So even in this game, well, as you'll see, the adversary can win, but not by too much. Okay, so this is the notion of swap omni prediction.
So beforehand, it was the same C in all parts.
Beforehand, it was the same C and the same L everywhere. Now they get to first see the partition and say, well, here I'm going to go with this L and this C. Here I'm going to go with that L and that C. Right? Okay, so an LC swap omni predictor is a predictor that's so good that no adversary can get significantly lower expected loss. The first thing I want to convince you of, okay, so this is inspired by the notion of swap regret in online learning from this famous work of Foster, Vora, and Blum-Mansur. I'll explain what exactly this means in a couple of slides.
Can I ask a question?
Of course.
So, thinking of this as a game for the adversary,
Yeah.
doesn't this like motivate you to like perturb slightly the partition of the space so that the adversary will have a harder time? I mean, is this like a good notion for saying something, for saying that something is better at predicting? Or
Okay.
because it looks like, we're changing the game so much that like.
You think it's become easy for the adversary now?
Oh, no, I'm not saying it becomes easy for the adversary.
It looks like
Saying
it
that,
becomes
like,
easy.
you tell me that something is a swapped omni predictor,
How could you do that, right?
I'm asking like, do I intuitively think that this should be like better than something that you haven't told me that it's a swap omni predictor?
It's
Like the
okay.
test is like so,
Yeah. So let me go ahead a couple of slides and see if I have a satisfactory answer for you or not. Otherwise, ask me the question again. Okay. So what is the swap omni prediction? So the first thing I want to convince you of is that it's a much stronger notion than omni prediction. I mean, I'm sure you guys see it already, but let's just go through it. Let's just consider the simple example of squared loss. Let's restrict the adversary to just predicting a constant value, 0, 1. That's all the adversary gets to do. Now, imagine that this was the predictor. All these partitions are equally likely. So what is the best strategy for the adversary? When you're minimizing squared loss, you just predict the expectation. And if I've done this correctly, the expectation here is 0.5. So the adversary will predict 0.5, they'll suffer a certain squared loss, which is much worse than the predictor. Because when the predictor says 0.1, they are doing significantly better than the adversary who's saying 0.5. This is a simple variance decomposition argument. So here in Omni prediction, the predictor can really do much better than the adversary. How about swap Omni prediction now? Do we see a strategy for the adversary which does at least as well? Well, sure, the adversary can just mimic what the predictor says. And now imagine that they are not just predicting with a constant, they're using a decision tree or a neural net. Right? You think they should be able to kick the predictor's butt, right? Well, the answer, so yes, in general, they can have lower loss. Can they do significantly better? This is basically asking, is the predictor C multi-calibrated? The advantage that the adversary gains over the predictor is tightly characterized by the multi-calibration error. The multi-calibration error is just for each partition. You look at the advantage, take the expectation. So the theorem that we show here is that P being C multi-calibrated is equivalent to it being an L convex, C swap on the predictor. Okay. Technically, there is a notion called swap multi-calibration that it's equivalent to, but it's really a technicality. You know, the notion, the way I defined it, is already the swap notion, so let's ignore that. Multi-calibration is equivalent to this notion of swap omniprediction.
So that means that if the multi-calibration is zero error, then you don't lose anything.
Yes, yes. If it's alpha, then it's up to quadratic factors of 4th degree or something like that. Okay. All right. So how do we, this seems like a really powerful statement, right? And, you know, how do you prove such a statement? Well, there are two directions you need to prove. That if it's not multi-calibrated, then you can improve on this, adversary can win. And that if it is multi-calibrated, the adversary cannot win. Both of these directions, surprisingly, are proved by the same one very powerful proof technique, which I will now share with you. You look at previous papers, and you see that they're proving something much more powerful, which is exactly what you want. So for instance, if P is not multi-calibrated, you can reduce the squared loss. Why is that? Well, this is basically how this algorithm of HKRR, the original algorithm, works. Let me just show you really quick. If you've seen gradient descent in any form, then this is familiar to you, right? So conditioned on some V, we have some correlation with the residues. Expectations V, Cx minus 0.3, conditioned on Px equals 0.3 is greater than equal to alpha. Pravesh, can you see this? Okay, good. So, no, I was just making sure you're not wrong. Suppose this is the case, right? In that case, if it's greater than alpha, in that case, I can update my predictor on this slice to say something like 0.3 plus alpha times Cx. It's either plus or minus alpha. One of the two will work. You do this small nudging of your predictor, and you will gain in squared error. So there is an advantage here. There is an obvious way in which the So what does this mean? If this is a hypothesis that the adversary can use, right? If C is closed under these kinds of simple linear combinations, then the adversary can do better than the multi-calibrated predictor. Sorry, did I do this too fast? So this is basically, this is basically gradient descent for squared loss. If you have correlation, that means you have a gradient direction where you can improve your predictions. That's exactly what you do. In the other direction, we want to show that if P is multi-calibrated, the adversary cannot do better than us for any convex loss function. But this is basically what this proof did. We just took a partition, then we argued that for any loss function and any C, you cannot do better. So we were already proving the strongest statement here. Okay, so this is kind of a very nice statement because it takes multi-calibration and tightly characterizes it in terms of convex loss minimization. It says that it's equivalent to this very strong notion called swap omniprediction. And another way of thinking about what this gives us a different way of thinking about what multi-calibration itself means. It means when you make a prediction, you don't feel the need to replace this with anything in C, be it constants, be it more complicated hypothesis. This is very similar to what calibration itself says. Calibration says that if I'm trying to minimize squared loss, when I say 0.3, I don't feel like I should have said 0.4 because condition on my saying 0.3, the true label in expectation is 0.3, right? So this is extending this characterization to multi-calibration.
So maybe you answered this already, but do you need C to be closed under some
I think, yeah, because I will do this much. I want to be able to nudge it at least like this. Yeah.
But for every C that has that closure property, this holds.
Correct. I might be hiding something. No, I think that's all. Okay. So another thing this tells us is that because multi-calibration is strong enough to give us this notion of swap omniprediction, which we all agreed is stronger than omniprediction, it's unlikely that it's actually necessary just for the vanilla version of omniprediction. Right? This is, well, it's indirect. We'd like to make a more direct statement here, but we'd also like to ask, maybe something weaker is necessary for omniprediction. Like maybe you just need calibration. Maybe you at least need multi-accuracy, right? Maybe one of these, multi-calibration is not necessary, but maybe something weaker is necessary. So I'll just show you a very quick proof that actually that's not the case, at least for these two notions, and then we'll break, right? Okay, so the bottom line is that omnipredictors are very plentiful, surprisingly. It's just that our only way of getting our hands on one of these things efficiently is by using these multi-group notions. Right? So let's talk about some simple closure properties of omnipredictors, and this will immediately answer the question we had on the previous slide. So what have I drawn here? Well, nothing much. So this is meant to be points. There's 6 points in our space. The y-axis is the predictions. They lie between 0 and 1. These red stars are the base optimal. So they're predicting certain values for our 6 points. The blue points are the predictions of our omnipredictor, right? So omniprediction, it's a computational notion. It's very easy to come up with concrete examples where you have an omnipredictor which is very far in total variation distance from base optimal. So let's fix an omnipredictor like that. Now, what is a simple operation that preserves this omniprediction property? So I'm predicting these blue values, right? But let's say an all-powerful being, Avi, comes and whispers in my ear that actually, when you're predicting 0.7, the right answer is 0.9, and where you predicted 0.1, it's 0.3. So naturally, I feel like I can cheat a little. I can nudge my predictions in the directions of base optimal. And this has to be only better, right? I was saying 0.7, I was already doing better than C. The truth is 0.9. Let me say 0.8, or maybe let me just say 0.9. So this operation of nudging your predictions in the direction of base optimal, sorry, I have some animation, yes. I can move all my values towards the base optimal pointwise, and this will preserve omniprediction. Is this like convex combinations? No, it's much more powerful because you can decide what to do for each and every point separately. So what I did here is that I only took the points which were originally lower than the base optimal. I moved those points up, right? Everything that was less than base optimal, I moved it up. The points which were higher, I let them be. So what did this do overall to my expected prediction? It went up considerably, right? So this tells us that there are omnipredictors which are not even accurate in expectation. Right? But if they are not accurate in expectation, they are not calibrated because calibration implies a detailed form of accuracy in expectation. They are not multi-accurate either because, if your C contains the constant 1 function, then accuracy in expectation is implied by this. So the point here is that the set of omnipredictors is surprisingly plentiful. And so this is work with Omer that we haven't even written up here, but it just says that omniprediction itself is this very broad thing. You don't need calibration, you don't need multi-accuracy, you don't even need accuracy and expectation for it.
That's
So-
the same thing would apply to swap on omniprediction.
Swap omniprediction.
Can't you improve their performance by nudging them towards the base optimum?
I'm not sure because, no, I'm not sure because your level sets might get messed up when you're moving points separately and so on. So, I mean, yeah, so I don't see that this argument should work. I have a paper which says it shouldn't work because multi-calibration is necessary. So it would be a big problem if it did. But you cannot move these points px, then you're shattering the level sets, right? The moment you shatter the level sets, my current, multi-calibration goes out of the window, right? Now, look, I had all these points where I was predicting 0.4. This was multi-calibrated. What you decided to do is to take some set of these points and make them 0.5. Take these points and make them or leave them at 0.4 even. I have no guarantee of multi-calibration on this because, there's this new partition now and I need to worry about, well, maybe there's correlations with this partition.
No, but you just want to do. You just want to do better on any loss function. Now you want to do is your loss functions that are specific to the different levels.
Yeah.
They may change as well.
So C had no correlation between these things. But, suppose I came up with some magic partition and said, now try. You might find correlations on both these halves. Just previously, they were canceling out. Right? All right. So congratulations. We've made it successfully to the... Okay. So what did we summarize the first? This is not half. It's 3/4 of the talk. Multi-calibration implies omniprediction for convex losses. In fact, it's equivalent to swap omniprediction. And omniprediction, the vanilla version, it's very hard to think of what could be a necessary condition for it, since it does not even require accuracy and expectation. Yet the only way we know how to achieve it is with the heavy hammer of multi-calibration. Let's take a break and we'll meet here in 10 minutes.
It's like,
An early lunch.
I don't think my question,
Yeah.
I think it's maybe opposite. Like this notion of swap the only prediction. But look, it's equivalent to calibrations, yeah. That's the power. But at least the like, if you tell me want your test to depend on level sets of P, the more complex P is, then like the Sure. So the test becomes we're giving a different loss to different sets. So we could a priori be like swap multi.
is it different than what we
achieve this
discussed
best,
the GCD?
making the sets weird enough so that C will perform badly on I honestly couldn't remember. Performing better yourself.
I think motivations
I think it's similar. I just.
I'm just saying,
I've
I've carefully
we were talking about
collected
three
each of
and we
these
were
sets, points, and
Yeah,
how
well, we-
correlations cancel
so
out.
you know that.
If you do a perturbation, it becomes something like this. Then now you're splitting this and say, here, do it
We
separately
all
of each of
assume
these
there are
things, and that's
multiple
more power to the
each
adversary, right? So I don't.
We
sorry,
removed
I-
the multiple.
I'm saying don't do
And then it looks
like
similar.
don't split the sets.
We are now.
Swap some of the
Yeah.
swap some
So I
of
was,
the
I was really thinking in terms of
three or something.
the family of.
Like maybe this makes
what
it
is the class of.
like much better.
Yeah.
Whereas you maybe.
That's what that, well, that's of course an important special
But
case.
see, that's the thing, right? It's not multi-calibration.
No, I agree with
At
that.
least justification, so it's not.
Right, I mean, obviously it's stronger.
Yeah, it's
like
concrete,
But I like this
Like,
more general version of the, we have this thresholding thing.
Yeah.
But really what it's saying is.
Okay, I mean, in retrospect, you answered the question, that's one thing that,
No, no, but
like, it's,
why didn't you see if you have a.
yeah, but.
Why don't we talk after?
We want
if you
in
have
and
questions?
out, and this is a simple
Like
function.
to think about.
Rather than
Right.
coordinate or the values in each particular coordinate.
Right.
Then this is one of the functions we can compute. I mean, it's a symmetric function. It's really the end in this case, and we can do exclusive over.
Yeah, we can do all.
Yeah, okay. No, but it's good to come there. Of course, that's an important topic.
Right.
If I step out, will I be able to come back in?
Yeah.
Okay, good. So I have to step out for a minute.
Before 5 p.m. though.
Thanks for letting me know. In which time zone?
Yeah, I just couldn't remember
It's
what we had said about.
it's good. Yeah, no, it's a good concrete example which we anyway need. Yeah, I think that well, I wrote in this email what I think, what I remember we discussed about the
Right.
the closure properties of the
Right. Like what are the functions?
the family of functions we can compute.
Yeah.
It would be nice at the end to say, GCD of polynomials and functions. Whatever.
Right. No, I think.
LCM is all.
Yeah.
This kind of
To have something that's so.
after multilinearizing, so you want you have multiples, get rid of them, or like this is a Booleanization operation, right? Take integers and
And just project them to 0, 1. Yeah.
But we do need the multiplicity because the GCD,
The GCD.
so these minimum operations, so minimum operations.
Yeah, we can do minimum, maximum.
Yeah.
Yeah, trying to understand.
You are already doing the multiple as well, I guess.
Right.
But we can I think there are probably more than one way.
I think so, yeah.
We can get, let's say, the GCD.
Right.
We can Booleanize, get the roots right, and then get the multiples right.
Right.
If you want.
Yeah. No, but I agree. I think getting some understanding of what are the things we can really do.
It'd be nice to, find some example of non-classical operations for non-classical.
Yeah.
Maybe it's meaningful. I don't know exclusive of that. I mean, for exclusive of not on two, but on three.
Yeah, I don't.
Very bizarre what's said about it.
Right. It's a strange operation. I mean, we can do it, but the question is why? What does this give you?
There's an intuition right for integers, it should not be parallel.
I just don't.
Well, there's no linear algebra like this.
Yeah. Is there any reasonable analog of what the power sums would be? If I give you
No, I don't think that. Somehow polynomial comes with a set, and an integer doesn't come with a set.
So
And the set of roots.
if I give you an n-bit integer, can you compute, say, n bits or 2n bits of its logarithm quickly? Because that's in some sense what.
Yeah. Only compute log n bit.
Right.
Is it? No, I don't know. I mean, it's a good question. Yeah, so it's polynomial time, but I don't see how to parallel.
What was your question?
Yeah, you just want, I give you an n-bit integer, you want the logarithm, but 2 n-bits of precision.
My guess is you can do log n parallel. Like somehow intuitively, you should be able to like square your error or something, but like I don't know exactly what I'm saying.
Really? I think
Newton-
By something like Newton,
yeah.
yeah.
Parallelized.
You should be able to go from error epsilon to error epsilon squared by doing like a Newton step. I don't exactly know what that means. 'Cause I haven't
But
done
this, no, but if you are doing this in sequential. You
No,
need
but
just a
you only need log
logarithmic
n
number
steps
of,
of Newton.
this is just, I don't know.
Be enough. You're right, something like that should be.
Yeah, you think it's Newton step with a square, yeah,
Yeah,
maybe you're right.
yeah.
No, but we are looking, doesn't help. We are looking for n bits, so we need 2 to the n to the minus n precision. So squaring the error is just going to take a linear number of steps.
No,
So
you're doubling the bits.
you
of
are
precision.
doubling the bits, yeah.
Or-
Okay.
Comes
Yeah,
away.
yeah. Yeah, no, it's on the road. So we're starting,
This is what time does to you.
okay?
I remember the lake, but I forgot about the geese. All right, welcome back. So far we've seen like, this basic result about Omni prediction and so on. So the question we want to ask now is that a lot of these, we agreed that everything we're doing here has a flavor of pseudo-randomness, right? So is there an indistinguishability based explanation for Omni prediction? That's the next question we want to ask. So what exactly do we mean by indistinguishability here? We're going to use this very elegant work by Dwork, Kim, Reingold, Rothblum, and Yona, where they introduced this notion called outcome indistinguishability. So this is one of these works which, starts from first principles. It asks, what does it mean for a predictor P tilde to be correct, right? Loss minimization gives you one answer, that it's close in a certain sense to the base optimal. They come up with a very refreshingly different take. They say that it ought to mean that the predicted outcomes are indistinguishable from nature. What exactly does this mean? Well, let's imagine that our goal here is to distinguish between two worlds. One is the world of nature or reality, where your labels are actually being drawn according to the true nature. The other is the matrix or the simulation, where we have a predictor. The labels are actually being drawn according to the predictor. Now we can imagine a distinguisher which gets access to the point x, the prediction value, and then a label. And what it needs to tell is, are these labels coming from nature or are they being drawn from the simulation, right? A distinguisher is just a function which takes these inputs, it maps to -1, 1. And the distinguisher wins if the expectation is very different under these two distributions, right? The standard notion of a distinguisher in pseudo-randomness. Models are good in this worldview if they are indistinguishable to fairly powerful families of distinguishers, right? So what does this notion of...
So until now, all your notions were information theoretics. Now it's the first time. I'm not talking about efficiency in finding but the calibration, multi-calibration, they are information theoretic notions.
Correct. Let me tell you what I'm going to tell you, and let's see if that, you see, this is my go-to move to just advance the slides for every question. But I want to try and answer that question properly. Basically, what they said is that this is not a new notion in some sense. Indistinguishability here is basically the same as multi-group fairness for a certain family of functions, right? In this world, where you get all these three things, it's the same as multi-calibration. Multi-calibration for what C, that will depend on what family of distinguishers you have here, right? If you do not show me X, you just show me PX and Y, then this basically indistinguishability here is just calibration. And let's see why that is. We have a prediction PX, right? In the simulated world, conditioned on PX, the label will be a Bernoulli draw with that parameter. What happens in the real world? Conditioned on PX, if you're calibrated, then Y is a Bernoulli draw with that probability of P. So these distributions are identical. Similarly, if you did not show me this, you just showed me X and Y, then you'll get multi-accuracy for an approach. So this is, just a translation. You just write it down, you get the same thing. So now the question of whether it can be done efficiently becomes a computational thing about whether you can do multi-calibration, multi-accuracy for that family. Okay, does that answer your question?
Yeah.
Good. Okay, so this notion, we are going to use it towards omniprediction. We're going to come up with this new definition, a lot of those in the stock, called loss outcome indistinguishability or loss OE, right? It's again parameterized by L and C, just like Omni prediction. What it says is that we are playing the same game of measuring the expected loss for the predictor and the adversary. Neither of them is able to tell the difference between Y star and the simulated labels, Y tilde. What exactly does this mean for the world of Omni prediction? Omni prediction is a statement about these two quantities.
So, Roy, can you go over the definition of loss OE?
Yeah, it's going to be in this slide. This is just, so, okay. So let's see. In Omni prediction, what do? We have a loss function L, which comes from this family N. We compute the expected loss of the predictor for this loss function. I just dropped the KL. Let's assume the loss is proper. We want to compare it with this quantity, which is the expected loss under L for the hypothesis C, where C comes from this class C. Loss OE is the condition that for all such L and all such C, when I switch to the simulated labels, nothing changes. The expectation stays the same. So that the loss that the predictor suffers when the labels are coming from the simulated distribution. And
Simulated is what piece?
it's Bernoulli according, it's what P says. Yes, exactly. Similarly, so this is just a definition. I haven't told you at all how you're going to go about achieving this. But the definition is that the predictor cannot tell the difference between the true labels and the predicted labels. And nor can the adversary, who's using a hypothesis from the class C. Even for the adversary, the expected losses are the same. If you can achieve this, I claim that you're getting Omni prediction in a very, conceptually simple manner. Why is that? Omni prediction is the claim that the predictor is doing better than the adversary. We want to prove it with Y star, but how about we try and prove it in the simulated world? In the simulated world, the predictor has a huge advantage, which is that this is a world of their creation. If they say P tilde, that's exactly what's going to happen. So in this world, the predictor is base optimal. So it is an Omni predictor. So you get this inequality in the simulated world. And if you manage to get these two equalities to hold, then you also get it in the real world.
Yeah, but in the real world, it only means that some efficient process cannot tell, they cannot find a place where the adversary beats the predictor.
Oh, no. So
you said indistinguishable, no? Oh, this. You have equal,
Oh, sorry. It's not computational indistinguishability. Like they have the same
the same value.
the same value. They have the same expected loss.
But you had the distinguisher before, so what were the?
Where are the
where is it-
distinguishers here? So what do we need for this equality? That's a question of what tests do we need to fool.
L is the test, no? Or am I getting it wrong?
You're almost there. The tests depend on L and on C. Let's see. This part, I claim that you just need calibration and you have this equality. Well, why is that? As I was telling you just one slide back, calibration is the following indistinguishability condition. It's the condition that the joint distribution of Y star and the prediction is identical.
If you write in white, then the people watching will be happier.
If I
Use white rather than blue.
use white rather than blue. Okay, sure. Okay. So calibration, I can state it equivalently as the following condition. The joint distribution of Y star and my predictions P tilde is identical to the distribution of, the simulation and P tilde X. Right? This is the simple conditioning argument where I fix a prediction value. This is a Bernoulli random variable with the same parameter. That is exactly what calibration says, that when I fix this, then Y star is also Bernoulli with the same parameter. So these two distributions are identical. Here, what are we doing? We're just applying some function looking at its expectation. First, they'll be identical. Right? So this was just calibration. What distinguishers do we need to fool here? Well, you can imagine that it's some distinguisher which depends both on L and C. Right? It turns out what you need is multi-accuracy. But the multi-accuracy may not be for C itself. You might have to post-process C by some family of functions that depends upon the loss. Right? For instance, you might need multi-accuracy for low powers of C. You might need it for C squared, C cubed, and so on. And again, let me tell you where this comes about. It's again, it's just a matter of writing things down. The only thing we'll use here is the fact that Y is Boolean, so the loss has a multilinear expansion. So we have this loss function, Ly, T, right, which is the loss you suffered. I can write this as the loss you suffer at 0 plus, let's call it the partial derivative of the loss times Y, where this is like the discrete derivative in Boolean function analysis. It's L10, L1t minus L0t. Right? So basically all this does is when Y is equal to 0, you get L0. When Y is equal to 1, you get L0 plus L1 minus L0, which is anyway. There is some function of t here. Right? And now if I want the expectation of this loss to be the same under Y star and Y tilde, right? You do the difference, you can just use this to write expectation Ly star Cx minus Ly tilde Cx is equal to the expectation of partial of L composed with C of X times Y star minus Y tilde. I'm only doing this to convince you that this is just a routine symbol pushing thing, right? There's some function depending on t. For instance, if t were the squared loss, this would look like 1 minus t squared minus t squared, which is 1 minus 2t. For every loss, it's some function. You need to compose that with C, get multi-accuracy for that. Okay. So what do we do when we get all this together? If you can achieve calibration and multi-accuracy for this class C prime, then you get omniprediction, but actually you get a much stronger condition in some sense, because omniprediction just asks that this inequality hold. We are proving the inequality in a very strong form. We're saying that, well, this is equal to this, that is equal to that, and the difference is not just positive. It's exactly what it would be in the simulated world, right? Okay. So this is the notion of loss OE. loss outcome indistinguishability. The nice thing about this is that this is more like a general technique. It's not like one result. You can apply it to any class L and C, by which again, I really mean any general class L of loss functions, as long as you're able to guarantee calibration and multi-accuracy for this class C prime, which is obtained by post-processing C in certain ways, you're good. You have this condition. And of course, the question is, well, how complex is this class C prime, right? Like if it's some extremely complicated, it is only post-processings of C, that's one thing. But you don't want it to be too complicated related to C.
Well, you will need, in particular, weak learners for C prime.
Exactly. That's the whole point, right? So you want a weak learner for C prime, which is why you're getting something stronger, but you might be making stronger assumptions. So we need to compare how these things work out. So there's a certain class of losses called matching losses, GLM losses. It includes things like the squared loss and the logistic loss, but what it is not important. Maybe what it is the class of losses for which this statement is true. For all these things, C prime is the same as C. There is no post-processing required, right? So in this case, what we're saying is that all you need is calibration and multi-accuracy, which is much weaker and much more efficient algorithmically than multi-calibration. Okay, so for these kinds of losses, we are getting, in some sense, we were complaining that the multi-calibration result doesn't scale down. We don't know how to do something easier for a smaller class of losses. Here we have a result like that, that for this class of losses, which I haven't told you exactly what they are, you don't need multi-calibration, you just need calibration and multi-accuracy. If you consider the class of all Lipschitz losses, not just convex losses, you could get away with a weak learner for or multi-accuracy for thresholds of C. So C is real valued now. Thresholds of C is some class of functions. Avi pointed out that a weak learner for thresholds of C might be a much stronger assumption than a weak learner for C itself. For example, if C is just single variables and their linear combinations, thresholds of C is half spaces, and learning half spaces is a much harder problem than learning just excise, right? What about convex Lipschitz losses? Well, the whole point is that in this indistinguishability framework, it's very hard to use convexity. We don't know how to say something simpler for convex Lipschitz losses as opposed to all Lipschitz losses. Because basically what happens is, I subtract two convex functions, and what structure does that give me? Not much, right? So, I mean, we've seen lots of theorems on indistinguishability in the pseudo-randomness literature. I don't know of any place where convexity plays a meaningful role, but okay.
Well, I mean, the minimax proof of the dense model theorem is uses convexity. I mean, it's different. Yeah, just of the set of simplex of probability distribution. This is, but it's another convexity than yours. It's,
but something that fools distinguishers, which are convex functions, but not other distinguishers. That kind of a statement. Yeah. So, I mean, we really started this project saying, oh, we're going to come up with a different and simpler proof using indistinguishability. What we got is a completely different creature, this loss OE notion. And in retrospect, I feel that it was morally flawed to look for an indistinguishability-based proof of the original result because it relies on convexity so heavily. But I'm happy to be proved wrong. Okay. Moreover, this technique is applicable to many other settings. There is some work on when you have other kinds of fairness constraints. You want an omnipredictor. There's this performative omniprediction. I can't tell you what it is because I'm not sure I know myself. And finally, there's this very recent work on regression, in the setting where the labels are real value. I'll take the next 20 minutes to tell you about this, and then we can all go to lunch. This is joint work with Princeville, Okorafor, Prasad Rakhavendra, Abhishek Shetty, and Mihir Singhal. It's very recent work. So before I tell you that, let's just summarize what we learned about loss OE. This is a stronger notion than omniprediction. And as I kind of told you already, that original statement we saw in the first half that multi-calibration gives you omniprediction for convex losses. It is not true that multi-calibration gives you loss OI for convex losses. You're getting the inequality you want, but it's not that the real world and the simulated world are indistinguishable. Let me show you why very quickly, because I'm sure that you guys will see this right away. Multi-calibration is a first order guarantee on C. This is really multi-accuracy, but it gives you this guarantee that Cx cannot tell the difference between Y star and Y tilde. If C is Boolean, this is independence, this is everything. If C is real, it's just a first order guarantee. It is very well possible that Cx squared can tell the difference between these two things. Very easy to come up with examples like this. Now you stare at this a little while and you make it an example where Y star minus Cx raised to 4 is different from Y tilde minus Cx raised to 4. Maybe Cx cubed, right? But basically the point I'm trying to make here is that when you do this, you'll get terms like Cx squared times Y star and so on. So in hindsight, there's no reason to expect that these would be indistinguishable. That you still get the inequality you want, that's luck. Okay. Any questions about this part?
But if Cx is convex, Cx squared is convex too. So it
No. C is not convex. C is just a function.
C, yeah, sorry, yeah.
C is a function.
The
The convex is the fourth power function.
Okay, good, yeah.
Okay. So we started off with omniprediction. I've told you about two stronger notions. I showed you swap omniprediction. I said that's stronger. I showed you loss OE. I said that's stronger than omniprediction. Look at this picture. It's begging for a maximal point in the lattice. It exists. It's called swap loss OE, where you combine both these ideas of OE and swap omniprediction. Implies both these notions. The interesting thing here is that both the swap notions, you can get tight characterizations in terms of multi-calibration. So this is getting into the complexity theory of omniprediction, which I'm not going to talk about more, but if you're interested, please come talk to me later. Let's switch to the setting of regression. This existence of omnipredictors itself, fairly surprising in my opinion. Okay, I know the base optimal is an omnipredictor. What happens in the world of regression? Should such a thing, by regression, I mean that the labels are real values in the interval 0, 1. It can be any bounded interval. Is there an analog of this theory in this setting? It's not obvious that even the base optimal predictor works, because what is a predictor in this setting? So let's talk about that. So we are not the first to ask this question. Fortunately, there's previous work in our community on this. We are in the setting where the distribution of y given x is a real variable in the interval 0, 1. We are not making any parametric assumptions, right? So it's not clear how you describe this distribution in finite length. The notion, a very natural notion of statistic predictors was put forward. This was formally defined, I think, by the latter paper, but it was implicitly defined in the case of moments by the former paper. Statistics correspond to just functions on the interval 0, 1, like y squared, and so on. Now, a prediction will try and tell you the expectations of these functions given x. One statistic predictor that we've already seen is the mean predictor. Because when I tell you that for the Boolean case, when I predict 0.7, what I mean is that there's a random variable y. It's Boolean, it's never taking the value 0.7, but that's its expectation. Right? Now, in the real case, I could tell you the first moment, the second moment, the third moment, at least what I expect them to be. That's what a statistic predictor is. And of course, why restrict ourselves to moments, right? You can have arbitrary functions. So a predictor, a statistics predictor, will predict expectations of functions. We've seen the mean.
Some specified family of functions.
Yeah, I'm not seeing it here, but I'm seeing it there. Very interesting. So moments are these. Another important family I want you to bear in mind is the CDF statistics, right? Which is a different generalization of what happened in the Boolean case. We have a real variable taking values in the interval 0, 1. I break it into epsilon width intervals and I tell you the probability that will fall in each of these buckets. This is kind of giving you the jagged approximation of the CDF. That's why I call them the CDF statistics. Okay. Now, our goal is omniprediction.
Is everything you said about Boolean holds for, suppose we were allowed 0, half, and 1.
Yeah, for k values.
Okay, but then this will extend.
Yes, for k values, you can come up with analogs. You'll always pay exponential in k for these kinds of statements. So, but if they are discrete, right? If you take k discrete values, everything will generalize very clearly. But we are now interested in the real interval kind of setting. Okay. So now our goal for omniprediction is that we should come up with predictions that allow expected loss minimization for any loss from the family. This is our goal, right? So there is a communication kind of problem here that we can abstract from this. Alice has a distribution for X, a conditional distribution for X. She knows everything about this distribution, right? She wants to communicate this to Bob, and Bob is not in the world to gain knowledge. Bob wants to minimize a function, right? Bob has some loss function, L, Y, T. All that Bob cares about is finding the action which will allow him to minimize the expected loss.
Because the distribution is on the value Y.
It's on the value Y, yeah. So we should, for this purpose, just fix the X. Alice believes something about the distribution of Y given X. How can she communicate this to Bob in a way that lets Bob get what he wants, which is to approximate loss minimization, right? So what is the family of functions that Alice can communicate to Bob to allow him to do expected loss minimization?
For every L.
Yes, for every X.
For every L.
For every L, yeah. For every L in this family. And yeah. Okay. A sufficient set of statistics for L will allow Bob to do epsilon approximate loss minimization. So maybe it's good to do an example as always. Suppose Bob is interested in LP losses for low degree polynomials. Suppose all Bob cares about is the L4 loss, right? So that's y minus t raised to 4. And he wants to minimize this expectation. So now you could write out the binomial expansion of this and conclude that, well, knowing the first 4 moments of y is all the information Bob needs. And of course, you probably stare at it and say, well, actually, first 3 moments would suffice because for the squared loss, you need only the mean, right? Okay. But now we care about expressive classes of loss functions like convex losses, right? And that's where we're heading to. If Bob wants to minimize arbitrary convex loss functions, what does Alice need to tell? But before I get there, let me tell you some boilerplate stuff as to why this clean question is interesting. You can lift this theory of loss OI that I showed you to the regression setting. Once you find a nice set of statistics like the moments here, how would that go? You find a set of sufficient statistics S for your class L, right? And then you're going to learn an S predictor where for each point X, your predictor estimates these statistics. Now, if you think about it, there is some magic going on here, at least I think, even in the case when suppose these statistics were moments, right? For every point X, you'll either see that point 0 times or 1 time, and then you'll see one sample of Y. Okay? You don't have time to estimate these statistics. So what's going on here? Well, this is the power of generalization. Just like in the Boolean case, you only got 1 sample or 0 samples, but still you were able to generalize and say, here I expect Y to be 0.7, here I expect Y to be something else. So just like that, you can predict other functions also. I mean, there's nothing new here, but it still uses the power of learning and generalization. you'll come up with an S predictor, which says for every point, here's what I expect these functions to be like in expectation. Then, once you have such a notion, such a set of statistics, you can define calibration. Calibration says that conditioned on my predicting this vector of expectations, empirically, that's what happens, right? Like, for example, for the first two moments, it would say that when I say expectation of this is something and expectation of x squared is something else, over all those points, now you're aggregating a bunch of points together, and here's what you're actually seeing. Yeah. So this calibration is important because this is what keeps our predictor sane in some sense. We know that if you're predicting the first k moments, there's all kinds of moment inequalities which your predictor should satisfy, right? And if you said, well, I want your predictions to be feasible, there's probably a semi-definite program that you'd have to write for that and so on. We get around that, we say, I want it calibrated. So now if you make some predictions, it better be the case that there is a random variable which gives you this predicted vector of moments, right? It's the variable that you'll see conditioned on these predictors. Okay. So then we say that P is multi-accurate. If there's a definition of multi-accuracy also, which works for statistics, exactly the same thing. It's saying that there is the residual function, right? You see y, you take it squared, and you compare it with your predicted second moment. There should be no pattern there. Once you've done all this, you can prove a statement saying that calibrated multi-accuracy will give you loss OE. It's not entirely standard, but there's nothing, you work through it and you can prove it.
What's the C prime here?
What is C prime? C prime again will depend on the loss functions, and now in a more complicated way. Like in this example, you'd see higher powers, and you'd also need to think about multi-accuracy for powers of y, not just for y itself. So I was purposely hiding that, but yeah, there is some C prime. The thing I want to emphasize is that if you ask for calibration for a vector of D statistics, you need to condition on this vector of size D. So that's going to take you time and sample complexity exponential in D. If you want to do multi-accuracy, then, of course, you're doing calls to some weak learner that will scale polynomially in the number D. Bottom line, you really want to look for the smallest set of sufficient statistics that you can find, because all your efficiency is tied to that. In fact, it depends pretty exponentially on the number of statistics. Okay, so with this in mind, we can now try and frame a clean question about these sufficient statistics. We know what sufficient statistics are. It should allow Bob to minimize any loss from this function family, right? But we'll simplify this a little more. I want to think of Alice now just holding a distribution on 0, 1. I got rid of the x, and you'll see why that's legit. Bob, I'm going to simplify by saying Bob holds a family of functions on the interval 0, 1. All Bob cares about is knowing the expectation of each of these functions to within an additive epsilon. Previously, we had a function of y and an action t. Here, I'm just fixing the t and enumerating over all possible actions for Bob. So now he has a bigger family of functions. What he cares about is knowing the expectations to within epsilon. Alice, to give some concrete examples, let's think of one class flib, which is the family of all Lipschitz functions, and FCVX, which is the family of convex Lipschitz functions. These are the two families that I care about. Alice's job is to send Bob a set of expectations of functions which will allow him to do this task. So once again, Alice has some distribution on 0, 1. Bob has some family of functions. It's one of these two families. Alice doesn't know which specific function he has in that family. She's going to send him one message which will let him compute the expectation of his chosen function to within epsilon. Okay. Is the communication problem clear? Okay.
So this was, just a pure question. Was this studied by statisticians?
I believe we are the first to study it, but if this is not true, I will be this is a communication complexity.
It is a communication, but it's a question of course, you phrase it as, but it's really what information about the distribution do you need to give in order to solve this basic.
I take it that you think this is an extremely natural problem, and I agree. But I've been thinking about this even in the Boolean case. If Alice has a distribution on the Boolean hypercube, Bob has a set of parity functions on n variables. I do not know what the right amount of communication is.
Yeah, but that's not the question statisticians would answer.
Okay, this is a question.
But this is a question.
This is a question which is, as you'll see,
Even for one function, right?
even for one function, but one function is this well phrased.
One function you will send its expectation.
But I wanted to work for, so just that function,
Yeah, that's
just that.
fine,
Yeah, so one function, no. Okay. Okay.
Yeah, maybe, for random set of functions, probably you'll have to send the expectation of each.
Probably.
For a convex set, maybe you have to send it only for the extreme points, I don't know.
One slide ahead is fine, but 3 slides ahead is a bit much. We'll get there. I'm glad you like this question. If you had to ask me who has looked at this before, I think it's going to be our colleagues in communication complexity. And it's because of the way that I'm going to phrase the question, right? Having phrased this question, I'm going to constrain Alice's message in the following way. She's going to pick a set S of functions, which is an epsilon approximate basis for f, which means point-wise, for any f in this family, there exist coefficients such that a linear combination of s's will give you a uniform epsilon approximation. Okay. So the family of S is fixed. So for example, if F is the linear span of S's, then trivially this holds with epsilon is equal to 0. But we allow for epsilon error here, which is what makes this more than linear algebra. This is approximate rank, like the way we study it in communication complexity, right? So once again, it's an epsilon approximate basis if for every function, there's a linear combination of S's, which gives you an epsilon uniform approximation. Okay. What is the point of this? Well, it's obvious, right? Like for any distribution D now, Alice will just send the expectations for the basis. Bob can take a linear combination and get the expectation to within epsilon. Right? So it's clear that this is a very good solution to the problem Alice is trying to solve with Bob. And this is just a question about approximate rank.
But it seems like because you'll always have errors, the L1 norm of the coefficients, etc., would matter, right?
Good, excellent question. And I think you also know the answer that I'm really going to concentrate on the size of the basis, because if you find me a basis of size D, there exists a different basis which is well conditioned where the coefficients will be poly D in size. So the errors will be log D. So let's ignore the fact that you said that. It's an excellent point, and let's just focus on the dimension. Great question. Okay. So now the question we want to ask is, what is the dimension of the smallest basis for f, specifically for the family of Lipschitz functions and convex Lipschitz functions? We're almost at lunchtime, so I suggest that we all volunteer a guess for what these dimensions are going to be. We'll check our intuition and then we'll go eat. So let's start off with what the obvious upper bound is, right? So when f is Lipschitz, right? Shoot. It's giving away my punchline. Okay. When f is Lipschitz, you can just send the CDF statistics. Why is that?
You can just say what?
Send the CDF statistics.
In some, you break it to intervals.
Yeah, so basically in the functional approximation language, you have a Lipschitz function. The basis I'm choosing are these delta functions, right? And of course, they give you an epsilon approximation to every Lipschitz function. So these expectations are enough. This is 1 over epsilon many functions. This suffices for all Lipschitz functions. Of course, it suffices for convex Lipschitz functions. Okay. Test your intuition. Is this tight?
Oh, for the first or for the second?
I'll take either answer.
Yeah, I don't know, maybe some Chebyshev polynomial, for example.
For the first or the second?
For the first.
For the first. Okay. So I don't usually like to delve into papers and say which co-author did what, but Mihir Singhal is a first-year grad student at Berkeley. If you hear this name again, remember you heard it here first. So this bound is tight for F Lipschitz. You cannot do better than 1 over epsilon. The thing that I find surprising is that for convex functions, there is a basis of functions of size 1 over epsilon to the 2/3. Okay. And a long time ago, in this room here, Noga Alon was on the stage. This is, I'm showing how old I am, but April 15, 2008. Noga Alon was here. I was sitting right where you are. And he gave this beautiful talk about the approximate rank of the identity matrix. And as only Noga can, he gave this slew of applications to geometry, coding theory, and so on. I was like, wow, that's really beautiful. I would like to find another application for this. It took a while, but it turns out this 1 over epsilon to the 2/3 is tight, and the result basically relies heavily on Alon's lower bound. Okay, so sorry, where was I? The upshot of this is that you can get omnipredictors for regression for convex Lipschitz losses, which run in time exponential in 1 over epsilon to the 2/3, which is an improvement over the exponential in 1 over epsilon you'd get for all Lipschitz losses. I was pretty happy with this already, but this is even better. I really wanted to show you this proof, but I'm over time, so I think we'll just break here. We'll go for lunch, and I'm around today and tomorrow. I really like this proof, so I'm very happy to show it to, I was going to say that this will be the discrete math part of the seminar. Unfortunately, we didn't have time for it, but it's a very clean statement about convex.
Is there an explicit basis?
It is fairly explicit. What is the low rank approximation for the identity matrix? It all starts from there.
Polynomial. The low degree polynomial.
No, this is not a polynomial.
In the proof. You take the.
Oh, so why does the identity matrix have a low rank approximation? Firstly, if you haven't seen this before, this is the most interesting fact you learn from this talk. The n cross n identity matrix has surprisingly low rank epsilon approximations.
In what sense? What?
L infinity. So if I want a matrix, so this is the identity matrix, right? So I want a matrix which is every entry is off just by epsilon. I want an n cross n matrix where every entry is off from the identity matrix by epsilon.
Is it just Johnson-Lindenstraus?
Basically.
Yeah.
Or the existence of good error correcting codes. Yeah. So how explicit is this? Well, if you can construct the right codes, then it's explicit. And this is one tool in our construction. If I keep talking long enough, I'll basically tell you the construction. So I should stop right now. We can go for lunch, and I'm more than happy
You
to
can
show.
talk for 5 minutes. It's okay.
Okay, let me show you this proof. Can we? Yeah. Can we move this?
There must
screen up?
be a way. Sam, can we leave the.
This is the best trick. You preserve suspense for the end, and then obviously nobody can leave.
I'm at California time. It's 9:30. Who wants to eat lunch? Since I woke up at 5:30, you can eat lunch late. So, what is the theorem that you're going to prove? F 0, 1 to R is a convex Lipschitz function. Since it's Lipschitz, it cannot take on many different values. Let's just say it's bounded in the region -1, 1. Now my claim is that, so I want to prove that FCVX is all these functions. My claim is the epsilon dimension of FCVX is order 1 over epsilon to the 2/3 up to polylog factors. Okay. Let me define the ReLU functions, ReLU of y, ReLU I of y. What are these functions? Up till I times epsilon, they are 0, and then they grow linearly. So it's on the interval 0, 1, and the y-axis is also on the interval 0, 1. So it's 0 if y is less than epsilon, and it's y minus I epsilon otherwise. Okay. First claim is that it suffices to come up with epsilon uniform approximations for the ReLU family of functions. Why is that? Well, here's it. It's a convex function, right? I'm going to come up with the following piecewise linear approximation, where I take points which are multiples of epsilon, I form these chords, right? Let's say their slope is m1, m2, m3, and so on. The two things we know is that these are Lipschitz and these are convex. I claim that implies that -1 is less than m1, less than m2, is less than m1 over epsilon. Okay. Why is that? Well, that they're bounded in one is just Lipschitzness. And convexity means that the slope can only increase, right? So you go on incrementing from here to there. Okay. And the way to think about ReLUs is to think of their derivatives. Oh, so throughout, maybe I should say that first. Why do the ReLUs play such an important role in this proof? Two reasons. What is the derivative of the ReLU function? So I rubbed out the ReLU, I'm sorry about that. The derivative, excellent. The derivative of the ReLU is the step function. What is the second derivative of the ReLU? It's the derivative of the derivative, so it's the delta function, right? So you see that the delta functions are showing up. These are the rows of the identity matrix. Having said that, I won't reference these facts explicitly, but you'll see that in the proof, this is basically what's going on. What is special about convex Lipschitz functions versus all Lipschitz functions? It's the structure of their derivatives. Okay, so now what am I doing with this? I have these slopes. I'm going to use this to show that you just need to approximate ReLU functions. Let's assume that the function starts at 0. Okay, so now I can approximate it by m1 times ReLU 0 of y. ReLU 0 of y is a fancy way of saying just y, right? So m1 times y. I got this chord, but right now my function looks like this. So what do? I correct the slope. Yeah. So plus m2 minus m1 times the ReLU 1 of y by my notation, so on and so forth, right? At each place, we just keep on lifting the slope. What is the sum of the coefficients here? This coefficient is at most -1. After that, we have this telescopic sum, which sums to at most 2 or something like that. So a corollary is that epsilon over 3 approximation to ReLU implies epsilon approximation to FCDX. So we've reduced our task to approximating the ReLUs. So let's start here. Now, to make this a truly discrete math thing, I'm going to just rescale the x-axis and the y-axis, right? So now I'm going to redefine the ReLU sub I as a function on integers 0 through n, to integers 0 through n.
N is 1 over.
N is 1 over epsilon. Yeah. And now, okay, so what is ReLU I? So ReLU functions, ReLU sub I of x is equal to x minus I for x greater than I, and it's 0 otherwise. Okay. And of course, if I get an approximation for this, I can scale it down, right? So all I care about is an order 1 approximation two values. This, after stretching the axis and shrinking it back, is the same thing as an epsilon approximation. So because we will divide the y-axis by n, you'll get your epsilon approximation.
So, Parikshit, the approximate degree of value is not less than 1 over epsilon
You mean as a polynomial?
as a polynomial? I mean, clearly you're not doing polynomials, so it's got to be false, right? Like it's
No, it means I don't know enough about polynomials. No, but absolute value is hard, right? For Jackson's theorem is.
yeah, but you discretized. So in some epsilon width around the point where it shoots up, I will ignore. Just like how you approximate sine functions by polynomials.
So maybe there is a polynomial view of this, and I'd be happy to hear about it. I'm arguably going to do something simpler, but we shall see. Maybe there's, if the two of you say there's a polynomial approximation, I'm inclined to believe that there is a polynomial.
I also don't know this very well, but Adam Clivans has a paper on like polynomial approximations of ReLU.
Yes, he does, and life is too short to read all of his papers, but it's entirely. I meant to send this to him and you and ask if this is something which looks familiar. But why use Jackson's theorem when you can do it with our own two hands, right? Okay. Here is, okay. If it's not clear, I really like this proof. It's not my proof, but yeah. Let's look at the difference between two ReLU functions. Let's consider ReLU I minus ReLU J for I less than J. Okay. So lemma, ReLU I. So ReLU sub I x minus ReLU sub j x is equal to what? Yeah. So basically the difference of these two things, it shoots up linearly from I to j. At this point, they're both growing at the same rate, so it will level off, right? So ReLU I minus ReLU j looks like this. Okay. So okay, also I forgot to say one more thing. When I'm approximating the ReLUs, I only care about the grid points because everything is piecewise linear. If we get the grid points right, we'll wave our hands and say it's uniform epsilon approximation everywhere. So ReLU I minus ReLU j is the summation of the indicator that x is greater than, let me call it a new variable k, where k goes from I plus 1 through j. Since I only care about the grid points, basically I'm decomposing this as the sum of this, sum of this, sum of this, sum of this, sum of this. Okay. One could look at this and say that this is just the discrete analog of this fact here, that the derivative of the ReLU is the step function, right? How we're going to use this is to say that I can write ReLU j as ReLU I minus a few interval functions. At this point, we have reduced approximating the ReLUs to approximating these intervals, right? Which it's not clear it's a good idea, right? Like, why should intervals be particularly easy to approximate? But you probably see where this is going. What is the derivative? I can write on the surface.
Yeah.
Okay. So now I'm going to strive for a constant approximation to intervals. Now this proof, which is hiding back there, only used open intervals to the right. But we'll do all intervals, okay? Let's start off with intervals of length 1, because that is the hardest, right? How did we come up with a uniform approximation to all intervals? Right. Well,
So this comes back to that.
intervals are basically the rows of the identity matrix. Right? So the approximation comes from Johnson-Lindenstrauss. If you take an n cross k random matrix whose rows are all unit vectors, what are you going to see here? Each diagonal entry will be 1. The off-diagonal entries will be something like 1 over square root k. Let's say they're log n over square root k. we're going to lose so many log-n's that this will not kill us, right? And this is a k-dimensional column space. And by taking linear combinations of this, I got this matrix. Well, maybe I should say this row space, it spans all the interval functions, intervals of length 1, right? So let's just record this fact. K dimension gives error, which is log n over root k. As long as you're looking for error, which is not like root n, this is giving you something non-trivial. Okay. Now, of course, we did intervals of length 1, and we want to do arbitrary intervals. But really, this is, after this, you'll use the dyadic trick. You'll do intervals of all sizes. That's just repetition of coordinates. So let's say k-dimensional, with k dimensions, you can do not just intervals of length 1, but all intervals with error, which is polylog n over root k. K is going to be some polynomial in n, so we'll ignore these polylog n factors anyway. Okay. With this in hand, we're going to go back and stare at this, right? Instead of having all these values, what we're going to do, I realize okay, how do I do this? I'm sure there's a way. I just moved to a different board, maybe. No. As you can tell, I don't use whiteboards at all. So our strategy now is going to be the following. We'll take a few evenly spaced values, okay? So remember that we are on the integers 0 to n. We'll keep the spacing between values as n to the 1/3. So there is n to the 2/3 values for all multiples of n to the 1/3. I'll take these values. These I get for free. How do I get the other values? I'll reconstruct them using this formula. I'll sum up the intervals, right? I'll sum up all the intervals. How many intervals do I need to sum up? At most n to the 1/3. So my basis for intervals better give me 1 over n to the 1/3 approximations. So I'll take 1 over n to the 1/3 approximations for all intervals. And how much does that cost me? Well, it's hiding somewhere under here, but this is also order 4 tilde n to the 2/3 many functions, right? This is where the magic happens. I take this basis of size n to the 2/3, and then I can do every set of intervals using this one basis. So then what I'm basically doing is, this is a discrete analog of integration, right? We are summing up. So you integrate out the other values. By not doing too many intervals at a time, you're keeping the error under control. So you have n to the 2/3 values, n to the 2/3 basis for intervals. Put these together and you have your basis. What is perhaps also surprising is that this is tight. And since I've kept you so long, I'll also show you that argument. It's really simple. It's basically a second derivative argument. I'm going to make this matrix where here I have all the multiples of n to the 1/3, 2 times n to the 1/3 and so on. Then here I'll write down the value. Sorry, are you guys able to see this?
Yeah.
Okay, here I'll write down the values for the same multiples of n to the 1/3. Okay, so these are the rows of the matrix, the ReLU functions, these same ReLU functions which I had up there. I just evaluate them also at multiples of n to the 1/3. Now, let me take the first difference. Let's subtract each row from the one above it, okay? The difference of two values, if you take my word for it, you will get n to the 1/3, n to the 1/3 all over here.
The triangle.
Yeah, you'll get the...
Then when you subtract, you get identity.
Exactly. So let's do as Avi says, let's subtract again. We'll get the identity matrix with n to the 1/3 on the diagonals. Of course, even if I had uniform approximations, constant error approximations, I would get some constant error over here. So it wouldn't be too bad. Let's take out the n to the 1/3, right? So we have an epsilon is equal to 1 over n to the 1/3 approximation to the identity matrix of dimension n to the 1/3 cross n to the 1/3. N to the 2/3 cross n to the 2/3, sorry. I need this to be able to apply Alon's theorem. And Alon tells us that this requires dimension n to the 2/3. So this construction is tight. Okay, so this concludes everything I wanted to say. I forgot to put up one very important slide, which had the acknowledgements, but that's, can we get back on here? So
Well, you can say it.
I have,
Okay. You have a lot of technology.
I have a lot of technology. In the interest of a faster lunch, let me show you the slide. So let me just end by saying that this work started out in multi-group fairness, but by this time this area it's grown considerably. We've seen connections to pseudo-randomness. This recent paper connecting it to the hardcore lemma and dense model theorem that I'm really excited by. Deeper study of what calibration itself means. And everything I've said is joint work with a bunch of wonderful co-authors, some of them colleagues from long time back. Many of them are interns, fresh grad students who I really enjoyed working with. I want to thank all of them and thank you for your extreme patience.
All right. Okay, so we'll ask you questions at lunch.